Hello everyone, please welcome to today's Quantum Cosmos seminar. Today we have Nilay Kundu from IIT Kanpur. Nilay did his PhD from TIFR and then he did postdoctoral stints in HRI and YITP Kyoto. And today he will tell us about studying inflationary cosmological correlators using conformal symmetry in momentum space.
Okay, so let me start. First of all, I would like to thank Nirmala for giving me this opportunity here to speak about our recent work. Title of my talk is uh, studying inflationary cosmological correlators using conformal symmetry in momentum space. So I'll start by explaining what various things that has been mentioned here. For example, we will try to understand what is inflation, then we will try to understand what is cosmological correlators, and then at some point I should be able to convince you that using techniques of conformal symmetry in momentum space, we can learn a lot about cosmological correlators during inflation. So first of all, please feel free to stop me at any point if you have any questions or any comments. I would be happy to discuss them. So let me start with some quick introduction to inflation. So this is a fact that our universe is approximately homogeneous and isotropic at large scales, at cosmological scales, which tells us that the metric which gives us distance between 2 points in our universe can be written in this particular form, where this part is the spatial 3 dimensions given by coordinates x, y, and z, and then this factor over here is known as the scale factor, and I can change my coordinates where this a squared t scale factor can be written as a conformal factor sitting outside of this whole metric like this. So this happens to be the coordinate transformation. So I go from t xyz to eta xyz, and the metric is written like this. Sometimes this factor eta, which is also a measure of time, is known as the conformal time. So this metric also explains that our universe is expanding, and that expansion is measured by some parameter which is called the Hubble parameter, which is a derivative of the scale factor with divided by the scale factor. So we should understand that it's like a balloon which is being expanded, and then there are coordinates which are drawn on the surface of that balloon. And if there is some insect or some creature who is living on this balloon, so for him this universe expands. So this balloon gets expanded, and this x, y, z remains same for someone who is living on the surface of this expanding balloon. So that's called the co-moving coordinates. So, but physically, when we measure from some observer who is standing outside, who measures this distance, he will realize that a distance which was here like this has expanded because of the space-time itself, or the surface of the balloon in this case, has expanded, and we will call that physical distance. So physical distance will be this factor of this scale factor a multiplied by the co-moving distance. Now, the question that we are all asking, or we should be asking, is why was the early universe so homogeneous? Now, how do we know that? So, by observation, observation tells us about that fact that we observe cosmic microwave background. So, at some point in our universe, when it was just created, the plasma of electrons and protons, they were interacting with them, but the universe was expanding. So there was a competition between this reaction rate versus the expansion of the universe. And at some point, this photons which were created in this reaction started free streaming, and at that moment, this CMB, or this cosmic microwave background, has was developed or was originated, and since then, which is like something around 30 this years after the Big Bang, this was created, and since then it's free streaming to us. And although the photons were very highly energetic when it was created during this generation of cosmic microwave background, the cosmic expansion has kind of redshifted that, and the wavelength has stretched enough. So today what we see is an ambient temperature of around 2.73 Kelvin, and this is in the range of microwave radiation. So this is our kind of our this is a picture. This is a picture or a snapshot of the early universe that we can directly observe in our observational techniques like Planck's or large-scale survey or any kind of observations. And that tells us that if we look at different directions in the sky, the temperature is almost constant. This is 2.73 Kelvin, and that's why this question, that why was early universe so homogeneous? So why is it that in all directions the temperature was almost constant, like 2.7 Kelvin, and that kind of creates a problem, which is a problem of causality, and that's called the horizon problem. And the standard Big Bang cosmology fails to explain this. So let me explain how this works out. So this y-axis is the time, and this is our spatial direction. So let's say we are here at this point, which is today, and light from far from our universe, I mean, very far from the universe, was coming to us along this direction. And let's say this happens to be some time slice which was around that 380000 years after the Big Bang, which is at this point. This large scale this last scattering surface, or this CMB generation, was at this surface. So we are looking at this point, and photons are free streaming towards us, which we are seeing at this point. Now, this point, and then there is another point in our universe, in our sky. If we look at a different point, light will come from that direction as well to us. Now, if I draw the past light cone from this point, only this much at the instant of Big Bang was in causal contact to this point. Now then the question is, how would this point know that this point also has this much temperature? So this past light cones were not overlapping, so they were not in causal contact with each other. So that's the horizon problem, and inflation is an attractive idea that solves this problem. Now, and it explains the homogeneity and isotropy of our universe. So let's say what we should do. So inflation is an idea which tells that this Big Bang at this slice, which was from which the standard Big Bang cosmology started, the radiation dominated or matter dominated era started, was preceded by a time, some very tiny uh, time, for which what happened is that it kind of stretched the Big Bang singularity from this point to this point, which gave this past light cones, which were originating from these 2 points, overlap in the far past. And this gives us a mechanism to explain that since this point and this point were in causal contact in the past. So it's very natural for this point and this point to know that the temperature has to be 2.73 Kelvin. So that's how homogeneity and isotropy has been explained. So here, as we can see, that there is a discussion about causal contact, whether this point or this point were in causal contact with each other or not. So let me be more precise by saying that what should be the measure of whether two particles are causally connected or not. So there is one notion which is called the particle horizon or co-moving particle horizon, which tells us that this is the maximum distance that light can travel since the beginning. So in this picture, this or this, I mean, in some sense, this happens to be the particle horizon at this point. At this point, light can travel from here to here, and that gives us a measure of what we mean by causal contact of this point. Now, anything which is outside this particle horizon, which is roughly this size, couldn't have communicated with this point. It would never. So the statement is, if two particles are separated by a length which is greater than this particle horizon, co-moving particle horizon, they were never in causal contact in the past, and therefore this name horizon is being attached to this particle, this eta. As you can see, this is same as the conformal time, and somewhere we are using the speed of light c equals to 1. So there is this another length scale which you can talk about, which is the co-moving Hubble radius, which is given by this factor. Now this determines a local scale for causal behavior. Now what do we mean by that? What I mean by that is that if two particles are separated by a distance which is greater than this co-moving Hubble radius at present. If at present two particles are separated by a distance which is greater than this 1 over AH, or this A is the scale factor, H is the Hubble parameter, so then they are not in causal contact at present, but can interact in future. So what do we desire when we say that we need inflation? What we mean is that this eta, or the co-moving particle horizon, should be large than the co-moving Hubble radius at present, or when CMB formed. Now that means that particles cannot communicate at present, but they were in causal contacts early on. So for that, what we need is this 1 over H has to be very large at far past. So that,
Sir, we have a question.
yes,
This
yes,
1
please.
by h should be the separation between any two particles. Is that what you're saying?
I mean, if I want to say that there are two particles and I want to know whether they are at present communicating with each other, so the distance between them, the separation between them should be less than the Hubble radius at present. That's what I mean. So
Okay.
if you are examining whether two particles with a given separation can communicate with each other at present. So exactly what does this 1 over AH means? So this 1 over AH is like roughly 1 over A dot by A. So A cancels. So this is like dt over dA. Now dt over dA is this 1 over AH, and then you can see that if A changes from A to A plus A, that means roughly the scale factor doubles, so that dA is A. This is a change in A. So dt over dA equal to A. So this is basically tells you that 1 over AH measures the time required for the scale factor to be doubled. So that kind of measure. So this is a local scale for causal behavior if two particles are separated. So there is a subtlety in the difference between 1 over h and this eta. If two particles are separated by a distance which is larger than this eta, that means they were never in causal contact in past. There is no way two of them can know that, about something about each other. But this is a local scale, meaning something is not at causal contact today, but tomorrow they can be in causal contact. So what we want is that this 1 over h, which is this co-moving Hubble radius, to be very large at far past. So let me explain this. Well, okay. So okay, if we want that this 1 over ah should be very large at the past, then the standard matter that we know in our standard model of particle physics, which is radiation or matter, for them you can show very easily that this 1 over ah is related to some power of this scale factor given by this 1 over 3 omega, where this omega is pressure over energy density. And there is something called strong energy condition that tells us that any matter or any radiation or any matter, any sensible matter should satisfy the strong energy condition for which this quantity, this relation has to hold. So summary, that 1 over ah increases with time. That means 1 over ah cannot be larger in the past. But what inflation does is that it makes 1 over h decrease with time. That means, this Hubble radius is shrinking with time. So I think, this will be clear in this picture, where this x-axis is given by me time, cosmic evolution, and in this axis I'm plotting co-moving scales. So this line is telling us how. Is there a question? Okay. So this line tells us that how this 1 over ah, which is the co-moving Hubble radius, evolves with time. And after this line on this side, where we have standard Big Bang cosmology, 1 over ah increases with time. Okay, and then you think that there is some scale which is some co-moving scale, which can be separation between 2 points, can be length, some length separation between 2 points, or it can be some perturbation or some mode for which the wavelength is k. Now, if the wave number is given by k, so k is inversely proportional to the wavelength. So k inverse is the length scale associated with that mode. Now, even if universe is expanding, that mode or the length scale associated to that mode stays constant. And this 1 over h, which is a co-moving Hubble radius, increases like this. Now, this point is today, let's say. So today, this mode is well inside this horizon, meaning at this point, 1 over k is less than this 1 over ah. So this can have causal contacts. The separation between them is less than 1 over h, so they can be in causal contact with each other. But in the past, since 1 over h decreases in this direction, in the past at some point this was outside this horizon, sometime somewhere here or here or here. At this point, this separation lambda or 1 over k was greater than 1 over ah. So that means they were not in causal contact with each other. So that's the horizon problem. So the two particles couldn't have interacted with them in the far past because they were outside the horizon, and then there is no explanation for the homogeneity that we see in our universe. Now, what inflation does,
Sorry,
yes.
can you repeat this statements again? So this co-moving scale, what does it represent?
So co-moving scale, you can attach, let's say, separation between two particles, which is lambda.
Mhm.
That has nothing to do with the expansion of the universe. So that stays constant.
Okay.
I'm saying, co-moving, not the physical length scale,
Okay.
the
Okay.
co-moving length scale.
So I
Or,
have two particles at some fixed distance from each other, right?
yes,
And you're saying
yes.
that one of the particle goes beyond the Hubble radius at
No, no,
some
no,
point?
no. I'm saying that this separation
Mhm.
was more than the 1 over h at this point. Let's say I'm at this point.
Right.
At this point, my co-moving Hubble radius is 1 over h.
Right.
So if two particles has to be with causal contact with each other, their separation must be somewhere here.
Right.
But our cosmic evolution tells us that they were outside this,
Okay.
I mean, greater than 1 over h. So two particles separated by a distance lambda couldn't have in causal contact before a time.
Okay.
And now translate this to observations that we make by looking at this point of the sky or this point of the sky. So there is some separation between them, but when we observe them in the sky, we see each point in the sky in a 360-degree angle around us. Each of them are at 2.73 Kelvin. The cosmic microwave background has a radiation, the temperature is 2.73 Kelvin. So how come, two antipodal points knew that the other point is at 3.73 Kelvin? Just by this logic, if you focus on just this part of the diagram, they were outside the causal contact in the past.
Right. So
Okay.
inflation solves that problem. That's
So
right.
inflation solves that somehow. What it does, it reverses the evolution of 1 over h. So inflation is this part, the shaded region, where 1 over h decreases with time, or the Hubble sphere shrinks. So all modes which has some separation given by lambda, or inverse of the wave number or momentum, inverse momentum is length scale, right?
Right.
So they were all inside the Hubble radius at very, very, very far past.
Right.
Okay, so this is how this horizon problem is solved. So this behavior, this is what they've done, and what inflation achieves is that this a 1 over a naught h naught, which is, let's say, this mode, which is the size of the observable universe at present. At present, so each day we are seeing more and more of our universe because lights are coming to us from far and far away. So let's say at today, which is here, the size of the Hubble radius is 1 over a naught h naught. All that we need is at some point in the far past, when inflation started, which is given by this AI, all of our observable universe, the size of that, were within the Hubble radius at the beginning. So all of them were inside this line. So they were all in causal contact. They could interact with each other, and they could send signal that, let us all organize ourselves in a way that the temperature should be 2.73. Okay, so as we can see that these modes at some point crosses the horizon. So at this part of the cosmic evolution, it was outside the horizon. So no causal physics was affecting this part. And then they are recently, in recent times, they're all entering again inside the horizon, because after inflation ended here, the standard Big Bang cosmology started and the 1/8 started increasing. So each day we are seeing more and more modes entering, and we're seeing our so anyway, and so this inflation ended here, and at some point this CMB formed, and then there is somewhere today we are all here. And so for inflation, this 1/8 should decrease, d dt of that should be negative, and as you can see, d dt of this thing is given by minus of a double dot by a dot square. Now a dot square is a whole square, it has a definite sign, so a double dot has to be greater than 0. So a double dot is the acceleration with which our universe is expanding. So inflation was an accelerated expansion. Okay, and then we should ask, standard particles like radiation or matter that we see in our particle physics can explain.
Sir,
Yes, please.
sir, can you just kindly go to the previous slide, like
Yes.
where you were drawing that separation between the particles? You have written it as going like 1/k. Shouldn't that be 1/ak? Because only then we can
No,
have that k
this
matrix.
is co-moving scale. So 1/k is being compared with 1/ah. This is co-moving. Any length scale you give me, if I multiply with a, that becomes a physical length scale.
Then the co-moving scale, that for the length scale, that should also be 1/h, not 1/a.
No, 1/ah is physical, 1/ah is co-moving. So multiply with a cancels, 1/h, that is physical.
Okay.
Okay, so we should know that we should ask how to kind of write a model that will accommodate us with this accelerated expansion. So summary so far is that inflation is a dominant paradigm to explain approximate homogeneity and isotropy of our universe. This also provides mechanism for tiny fluctuations to break the homogeneity and isotropy. So I said that our universe is homogeneous and isotropic, but that's not exactly correct. There are tiny fluctuations. So you can see that the temperature difference. What is the difference? Difference between an observation here and an observation here. It's not exactly 2.73 Kelvin, but there are tiny fluctuations which are of the order of 10 to the minus 5. So inflation provides a mechanism that there are tiny fluctuations to be present, and they happens to be seed for future large-scale structures that we see today. And what we would like to measure is how these perturbations or these fluctuations are correlated at different directions. And that information of this correlation functions of these perturbations, that's encoded in the CMB. We can directly observe it in our observations. And then if we have some theoretical framework to explain this correlation functions of these perturbations, then we can directly compare with experiment. And one thing we should remember is that during that time when the universe was exponentially expanding, so space-time was getting stretched very, very, very violently. So it was definitely a quantum process involving gravity. So all we are learning here have quantum effects involving gravity. Now, how to model this inflation? So to model this inflation, for today's talk, we will focus into single field model of inflation, where we have a single scalar field with some potential, and then we have this Einstein Hilbert action in 4 space-time dimensions. So this happens to be the action for the model of inflation, and this potential v phi as a function of phi looks like this. So let's consider the particle, which is kind of so this potential is not exactly flat, but it's almost flat. So that means this guy is rolling here, it's slowly rolling here, and some point the potential is like this. So when it falls here, the kinetic energy, so at this point of particle's motion, the kinetic energy is dominated by the potential energy. Potential energy is very large, and at some point kinetic energy dominates over the potential energy. This part dominates over this part, and then at that point inflation ends, and then we enter into the standard Big Bang cosmology, when all the so this scalar field is called inflaton, and all the energy that this kinetic energy of this inflaton gets transformed into all our standard model particles like radiation or matter or anything, and that's called a phase of reheating, and then from there standard Big Bang cosmology starts. So we should be looking at the Einstein's equations, and on the right hand side we have some stress energy tensor, and that stress energy tensor for the scalar field can be written like this, which directly follows from this action over here, and this is some standard field theory calculation. You can verify that, and if our field is homogeneous, this inflaton field is homogeneous, that means it doesn't depend on the position. It's just a time dependent function. It's constant over x, y, z. That's why if it's homogeneous, then from the stress energy tensor, if you look at the 0 component of that, you get energy of the inflaton, and if you look at the spatial components of this stress energy tensor, II component, then you get what is called the pressure associated with that inflaton model, the scalar field model, and that turns out to be this one, where you can see that if the kinetic energy is much less than potential energy, that's the situation when inflation was happening. So this pressure becomes negative. So this is the weird feature of inflation, and that kind of justifies this fact that so it's not very natural to have particles or matter which have negative pressure. So this scalar field is a weird object which has this negative pressure. Now, why is that, and why is not? How to understand that? For that, one really needs to do a quantum theory of gravity and understand that. Otherwise, this is when we should understand that this is just a model, and in that model, with this particular action, we can at least explain the problems, and it matches perfectly, very nicely with the observation as well. So as I said, that this potential was almost constant during the inflation. Now, if it was exactly constant, that means there was no so this action happens to be just Einstein-Hilbert term and a cosmological constant, which is a positive cosmological constant. That means this potential is almost constant. Then this action happens to be the gravity with a positive cosmological constant, and the solution that we obtain from there is this, where the scale factor square is given by e to the power twice to ht, and that's why we say that during inflation, it was exponentially expanding. So therefore, this exponential function, and this h happens to be a constant, which is decided by this cosmological constant, and this metric or this space-time has a name which is called de Sitter space-time. So what we're trying to say here is that during inflation, our space-time was almost de Sitter. Now, why almost? Because, as I said, this potential is not exactly flat. So this h will, in real situation, in inflation, this h will not be a constant. It will vary with time, and that's also needed. Why is that needed? That's needed because otherwise it will never end. The inflation will never end. So if you have a slope, so at some point, the kinetic energy will start dominating and inflation will end. And as we have seen before, we need inflation to end at some point. It just needs to solve the problem, horizon problem, and then we transit to the standard Big Bang cosmology. So the thing that we should understand from here is that the space-time during inflation was almost de Sitter. This almost means this h was approximately constant. And therefore, we should now look at the symmetries of the de Sitter space. Now, why are we trying to do things with symmetries? Because symmetries are important, because otherwise what we would have to do is to assume different models of this potential. And we can calculate things with a given model, but if we can understand the symmetries that were present during this inflation, then we can probably not have to. So, doing it model by model is an open-ended problem. I mean, it will never end. There are thousands and lakhs and crores of models, and almost that you can come up with various models that can give you satisfactory answer, and then use observation to kind of keep some model or neglect some model. But the principle that I am trying to adopt here is to study the symmetries that were there, present there, such that we don't rely on particular models. So what were the symmetries of this metric that is given by what is called Killing vectors in general relativity? So this is a maximally symmetric spacetime, and for maximally symmetric spacetime, there were 10 Killing vectors. So you can figure out in 4 dimensions maximum number of symmetries that you can have is n into n plus 1 by 2 with n equal to 4, and that gives us 10. Amongst them, 3 are translations, 3 are rotations, 1 scaling, and 3 something called spatial conformal transformations. And you can write the generators of them. So as you can see, this is the generators corresponding to the translations. This corresponds to the generator of rotations. This corresponds to the generator of scaling, and these corresponds to the 3 spatial conformal transformations. This I index over here runs over 1, 2, 3, and eta is the conformal prime that is present here. And the algebra that is satisfied by these generators happens to be something called SO4, 1 special orthogonal group with 4, 1. So if you, why 4, 1? Because you can embed the de Sitter space, which is a 4-dimensional de Sitter space, in one higher dimensional 5-dimensional flat space as a hyperbolic slice in 5-dimensional flat space, but with 1 time and 4 space-like coordinates. That's why this 4, 1.
Sir,
Yes.
sir, we say that this is a CFT in 3 dimensions, but I think this should hold only for late times, right?
Yeah, that's what I will come. Yeah.
Okay.
Any other questions so far? Okay. So as we know that this de Sitter was not exactly the spacetime during inflation, so the symmetries are slightly broken, and 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 uh, and by which we mean that the scalar field has fluctuations across some background field. So the dynamical variables that we have are the metric during the spacetime. This metric g mu nu was approximately de Sitter, and we have a scalar field. And so this we have said before that during inflation, so for de Sitter, h happens to be a constant, but during inflation, h becomes time dependent. Now, how do we figure out why this I mean, how do we measure the departure or the deviation from exact de Sitter? So there are something called slow roll parameters, and as you can see, the slow roll parameters are given by the time derivative of the Hubble parameter or double time derivative. So if it was exactly de Sitter, h was constant, h would be constant, and the right hand side would be just 0. So to take de Sitter limit, we should have epsilon or delta to be exactly 0. But to what we're doing is kind of a perturbation theory in this epsilon and delta. And there is also this fact that the background time variation is small compared to the Hubble radius. So for the canonical slow roll model, where the Hubble is given by the potential like this, you can figure out that this parameter is not an independent parameter. By the equations of motion, you can relate this to this Hubble parameter, slow roll parameter epsilon. Actually, this is given by the square root of the slow roll parameter. Now, as I said, the metric was not exactly de Sitter, so the metric will have now perturbations. So let us write down the perturbations, because what we are going to study are these perturbations, the fluctuations and their correlation functions. Okay, so this was my if this is my metric, then you can see that this hij, which is the induced metric on the spatial sector, it has two perturbations given by the zeta and gamma ij. Now the zeta is a trace of this gamma ij part. So in other words, I have taken the trace out and I'm writing it exactly separately, and gamma ij happens to be traceless. So the trace part is a scalar function, and the gamma ij is a tensor perturbation. And the scalar field had a background which is given by fiber t, which was homogeneous. That's why it doesn't depend on x, y, z, but there are fluctuations of that scalar field also of the inflaton, and that is denoted by delta phi, which can be functions of x, y, and z. So in total, we have three perturbations: the zeta, delta phi, and gamma ij. Amongst these three of them, the zeta and gamma ij, they come from the metric perturbations, and the delta phi, that comes from the scalar sector. Now, if you
sorry,
yes,
can I just ask one question? So this
sure.
approximation that you took, that epsilon and delta has to be much less than 1.
Yes.
Will this approximation be still valid when you are exiting inflation, for example?
No. So when actually that's the thing. When these parameters will break, so this perturbative setup will break down, and that will denote the the end of inflation. We cannot apply the rules of inflation to study the universe anymore.
Oh, okay.
Exactly. So this is the validity conditions for the inflation.
Okay.
So as you can,
by the
yeah.
end of the inflation, the space-time does not look very close to de Sitter anymore, right?
Does not look very close to de Sitter.
Okay. Okay.
And also probably what you are hinting towards, is there a sharp transition from the end of inflation to the standard model of particle physics? I would say, well, there is no sharp transition that you can say that it ended at this point. All we can say is that there is a region for which this approximations will break, and then we have to move to a different, completely different. So that's why I'm saying this is a model, or this is an effective theory. So
Right.
we don't know the full quantum theory of gravity. There is no consistent. I mean, there are attempts, but there are problems to deal with, time dependent situations in any consistent theory of quantum gravity yet. So what we are trying to do is to come up with effective theories, and for effective theories we always have a region of validity. We cannot take an effective theory and take it to be valid to all energy scales or all time scales.
Right. Thank you.
Okay. So we have this fluctuations that we have defined, and then what you can do is you can take this metric, take this scalar field, put it back in this original action, and then you can linearize. Since they are small, you can find out the linearized action for these perturbations. So the background space-time meaning the de Sitter space plus the phi bar, this solves the equation of motion. So as we know, the linear order piece will vanish, because that's the that's the equation of motion. The linear order piece of the variation of the action is the equation of motion, and the background fields will satisfy the equation of motion. So there will be no linear order piece. Only the delta phi square, the quadratic order piece, will be there, and that quadratic order piece happens to be this, as you can see. So this looks like a free scalar field in de Sitter space. So that's why I'm telling you that even if the symmetries of the space-time are slightly broken, we can still study the perturbations as if they are like some free scalar field on top of a fixed exact de Sitter background. This is the conformal perturbation. Perturbation field. Okay, and if you look at the equation of motion, the Klein-Gordon equation of this scalar field just happens to be this. So you should be familiar with this term and this term. This term is actually the two time derivative, and this part is the spatial derivative. Now I've written it in momentum space, so each of this variation will bring down a factor of k in momentum space. So k square means I have a delta square. So these two pieces are known to us, but because of the expansion of the universe, we get a friction term. Now, let's say we want to study whether modes, this k will be, so this delta phi can be written in Fourier space, something like that, and then this delta phi will be a function of k. So the momentum will be a label for that mode, and that momentum k, whether that is less than ah or greater than ah, decides if the mode is inside the horizon or outside the horizon. So super horizon means that this mode length scale associated to the momentum, which is 1 over k, is much greater than the Hubble radius, and that's what we call super horizon. And for those cases, what you can see is that this is equivalent to this. So this term is very small, so you can neglect this term, and then the equation happens to be just these two terms, and then you see delta phi is a constant. So what we learn here is that super horizon modes freeze out, they become constant. Now let us come back to this figure again. So this was the time when inflation was happening, and there were perturbations which was like delta phi, gamma ij, and zeta. Now they were all evolving with time. Now at this point, the 1 over k became larger than the 1 over ah, and this region therefore is called the super horizon part. And that means when these modes crossed the horizon or exit the horizon, they freeze. If they freeze, then this part, there is no physics at all. They just stay constant. So at this point, the mode exits, and then it happens, it gets frozen, and then at some point it re-enters the causal physics part because it kind of gets inside the horizon. So again, physics can affect it. But by that time, inflation has ended. So if we are interested about physics of inflation, then all that we know is what was the situation at this slice. Now for this mode, this delta phi mode or whatever perturbations were here, whenever they crossed the horizon here or here or here, they gets frozen and just come straight to the re-entry. But the physics starting from here is well known. This is standard Big Bang cosmology. So if we know the mode here, then there are standard techniques. You can write down computer codes to kind of translate it to the CMB when the CMB was formed, and then today. Now, I'm not saying that this physics is non-trivial. Trivial. This is trivial. This is non-trivial, but known. We know how radiation in radiation dominated universe or matter dominated universe, any mode will evolve. But what we are all after is what happened during the inflation. Because of this super horizon mode getting frozen, we don't need to worry about what happens in this part, which is a long part of evolution. Whenever it exited, gets clicked, or you can get a snapshot of that just at this point is equivalent to this point. Okay. So now, so this de Sitter space-time was during this time when inflation was running. Sorry, Nimalo, how much?
Hello? Hello? Can anyone else hear Nilay?
Yeah, I can hear you. I think he got disconnected. So I think the internet in IIT Kanpur is down. Devanshuda just messaged me.
I see. So that's why a number of people suddenly were disconnected.
Hello.
We can hear you.
Okay. Sorry, I don't know what happened.
I think there's some internet
Probably a
issue
problem.
there
Yeah.
because Devanshu
No.
also got
Okay.
disconnected.
I see. I see. I see. So I was asking how much time do I have?
So you, I mean, this we have covered 1 hour. Take, I
Mm-hmm.
mean, we can continue for half an hour more. But if you think that
Okay.
we need more time, we can maybe stop now and have it like a second part another day. So both options are there.
So let me go ahead for 10 more minutes, and then
Okay.
I will see if I can.
Okay.
Okay. So I'm continuing. Okay. Okay. So yeah. So the late time slice of de-Sitter is where we are observing things. Okay. That's like end of inflation. This was de-Sitter, and whatever happened on this slice is what we observe in the CMB. That's what I explained. And in this conformal coordinates, conformal time coordinate, which is eta, eta runs from minus infinity at far past to eta equal to 0 at the end of inflation. So this slice is the end of inflation. Okay, and then uh, so then what happens is this perturbations are doing whatever they are doing here in the so this is all de-Sitter space, and when we take late time limit, says delta phi, gamma ij, and zeta, they will have some boundary value at the end of this inflation slice. So this is a spatial slice as eta equal to 0, and we look for correlation functions of 3-point functions in let's say 3-point function or 4-point function or 2-point function or any hard point function, and that we can connect with observation. Okay, so this delta phi, which is a metric perturbation or a scalar field perturbation, gets related to the temperature fluctuations that are imprinted or recorded on the CMB slice, and that's what we observe. So is that part clear? That the late time slice of de-Sitter 4 is what is important for us, and what we are observing are correlation functions on that slide. It can be 4-point function or 5-point function or 6-point function, 5-point function. Okay.
Sorry, but I thought
Yeah.
that at late times this de-Sitter approximation breaks down. So then,
Yeah. So after this, there is no de-Sitter. That's why de-Sitter ended at eta equals to 0.
okay,
But
but up
you
to
know,
it equal to 0, you can assume that it's still de-Sitter.
so
Like
this
those
part
epsilons and
is
deltas are still less than 1.
yes, yes. So in this region, I have eta equal to minus infinity here. Eta becomes eta equal to 0 here. This was de-Sitter 4, approximately de-Sitter 4 with Slorol parameters being there present, and we want to do whatever we want. But the late time slice of de-Sitter is here where the inflation ends, and that in this picture is kind of rotated by 90 degree, and that's what we see here.
Okay.
So when we are looking for de-Sitter physics, what we are doing is like doing quantum field theory in curved space-time. So I have gamma, ij, delta phi, or zeta, the tensor mode or scalar modes, and how do they evolve or how do they interact in a curved background. So this is quantum field theory in curved space-time on this side. Now this is all what we have explained so far. Now,
Sorry,
where,
can I ask one question?
Please.
Why are we taking a 3-point correlation function in this case?
Yeah. So there is no. I'm just just to pictorially depict it that this is a 3-point function, but you can definitely look for 4-point function, 5-point functions. All of them are, as you know, in cosmology termed as non-Gaussianities. So the Gaussian thing is just 2-point function. But then this 3-point function, 4-point function, 5-point function are higher. As it also, it can be said in a different way that CMB observations are like statistics. So in a statistical distribution, we get the 2-point moment or we higher point moments. All of them are needed. So I'm just for a pictorial depiction.
Okay, thank you.
And also, since you asked, so there is a way of understanding this also physically what is happening. So physically what is happening is that, you know, space time during this time is getting stretched very violently,
Mm-hmm.
and for that, uh, so this is a feature of quantum field theory in curved spacetime, that out of vacuum, three particles can generate from nowhere,
Okay.
from vacuum, because this is quantum field theory in curved spacetime. And then they all travel and they come and sit here. So yeah, so this is this very non-trivial physics that is going on in the bulk. Now, whether there are three particles or four particles, now there can be processes where, you know, two of them gets emitted, and then this gets again separated into two, this gets separated into two. So this is basically a 4-point function. So in the standard QFT language, this is like something like this exchange diagram, where these four are now points, endpoints are now attached to this time slice. So yeah, we all have to do, all that we have to do is, you know, doing Feynman diagrams, all possible Feynman diagrams and all for a quantum field theory cards.
Okay, thank you.
Yeah. So now comes the next part is, where does the CFT comes into play? What is this quantum conformal field theory has to do with all this story? So this was de Sitter physics. Now, as I've told you that this delta phi, gamma, ij, or zeta. So whenever I write something with delta phi, you should remember that this is a symbol to represent this this three of them, all three of them. Okay, so if you know the evolution equations of them in the bulk, and then if you take the late time limit, then there is a particular fall off of that field near eta equal to 0. So this is some function of x times eta to the power some delta. So at eta going to 0, this happens to be the value that you should attach to this late time slice. Okay, so these are the late time values of any mode. How do I get this? I get this by solving the bulk Klein-Gordon equation, for example, which I wrote a few slides before. And this delta is related to the mass of the scalar field in this way. Now, if you are doing massless field, put m equals to 0, then delta turns out to be 3. Okay, so this and then if you look at the generators that I wrote before and take this eta going to 0 limit, then you land up with this relations where these generators at eta going to 0, simply put eta equal to 0 wherever they are, and this will now operate on this late time value. So the relations that you get are this. Now this, those of you who are familiar with conformal field theory, this is how a primary operator with dimension delta transform in a conformal field theory. Okay, so all that we are saying is that in this slice there is a hypothetical conformal field theory for which I have various operators with some specific dimensions, and they are like the late time values of the bulk fields that are present in my QFT in curved spacetime. So there are two descriptions available here. There is a quantum field theory in curved spacetime or de Sitter, and on the late time slice of it, I can use techniques of conformal field theory to figure out the correlation functions. And as you know very well, in conformal field theory, 3-point functions or 4-point functions, they are known, like, you know, 2-point function and 3-point functions are completely fixed. 4-point function is fixed up to some cross ratios. All that technique we can see. So we are all of us are, I mean, we are after the correlation functions of fluctuations in the CMB. This is a CMB slice, if you can say. Now you can use this CFT technique on this. So that's where this conformal field theory comes in. And why momentum space? Because on this slice we roughly have homogeneity. Now if we have homogeneity, then using momentum space by just advantage of translational invariance of the constant time slice, it's very natural to organize things in momentum space. Okay, so all that we are trying to say is that in the CMB observation, we should apply conformal techniques of conformal symmetry. Now, what does observations say? Now, observations tell us that the correlation functions are scale invariant to a very precise accuracy. Now, scale invariance is not conformal invariance completely. So here we are trying to say that, okay, so if the observations say, support scale invariance, so let's try to use the techniques of use the full conformal group and constrain the correlation functions and then check them against observations. Okay, so this is how this O delta transform under this momentum space, and that you can say that in momentum in position space, and then you can write how these operators will transform under the action of generators of scaling and spatial conformal transformations in momentum space. So these are scalar operators, but you can also apply this to spinning operators. So we not only see temperature fluctuations in the CMB, but we also see gravity waves, primordial gravity waves. There are B modes or E modes of primordial gravity waves, certain polarizations of this gamma ij. There are two independent polarizations, B mode or E mode, and you can figure out the correlation functions between them also. And so we have two stories. In one side we have a de Sitter space, and there is a massless scalar field which corresponds to some operator O delta with delta equal to 3 in a three-dimensional conformal field theory. We can have a massless gauge field in de Sitter space that will correspond to a conserved current Ji with dimension delta equals to 2, and we can also have massless gravitons. This gamma ij is the gravity perturbations, and we can call it graviton. They will correspond to a stress tensor Tij with delta equals to 3, three-dimensional operators. So that brings us to this realization that correlation function of cosmological perturbations during inflation at the eta equals to 0 slice can be studied by using correlation functions in CFT in momentum space. Okay, so what do you suggest in Nirmal? Like this was all used in just setting up the.
Yes, so I think this may be a good time to stop, Nilay, because I think this kind of sets up the problem. If you want to continue, we can, but I think this is going really well. And
Yes. I mean now I can discuss my my own result or whatever we did in the last paper. This sets up the stage for that. I don't know if I went too slow. But
well, now it's up to you. I mean, if you
no, I can definitely
do it another time.
discuss in some other day.
So that would be
fine.
nice. Okay, so we can discuss the date later
Yes.
and fix something. So okay, so let us now thank Nilay for this excellent introduction to cosmology and correlators. And if you have any questions, please ask.
Can I ask a question?
Yes.
Are you imposing a bound on mass? As in delta can be complex, right?
Yes. So as you can see that, I didn't say this, but this is more or less those of you who are familiar with ADS CFT correspondence. There is one more mode which is here. which
I mean,
is, you know,
there is no, this is not like BF bound. I should not think of it like a BF bound like ADS.
no,
That
no,
is
this
my
is just a fall of
okay,
condition,
okay,
fall of condition of a scalar field in
okay,
LT0 space.
okay. Thank you.
But yeah, I deliberately didn't write the
Right,
other
right,
mode, which if this is eta delta plus, there should be eta delta minus,
right,
and I
right.
should have written delta plus minus and this delta plus minus. As you can see, as you know very well, probably, you know, this delta equals to 3 in D equals to 3 dimensions is related to the delta equal to 0 mode by something which is called the shadow transformation. But yeah, I didn't want to get into the details.
Sorry, may I ask a question?
Sure, sure.
What is the role of this delta operator? I mean, does this anything to do with, like, I mean, can we relate it to this thing called anomalous dimension operator? If I'm not wrong.
Exactly, exactly. So this delta is called the scaling dimension of this operator O delta in a CFT.
Mm-hmm.
But now, if you are you know, if you are looking at, so what we are doing is we are looking at this operator O, which has a dimension delta that tells us that if I scale my coordinates by x going to lambda times x, this operator O will scale like lambda to the power this power delta times O, and that's kind of captured by this equation over here, and you can relate these two. But now if you do QFT, and if you know, in quantum, if you look for quantum corrections, then this classical scaling dimension can change,
Okay.
and that's called the anomalous dimensions.
Okay.
But yeah, this is scaling dimension of this operator O.
Okay. Thank you.
But you know, if you are not familiar, if you are not willing to discuss about CFT and all, this is just packaging the information of the mass
Okay. Okay.
of the bulk field.
And those masses of the inflatons?
Mass of the inflator, yes.
Yeah, hi, Nilada. So one
Hi,
question
yes,
is like,
yes.
can you please repeat the argument why the safety in momentum space is necessary? I mean, in this, just you argued
Yeah.
something, but
So,
yeah, I just missed.
yes.
Yeah.
So as you can see, you know, we can very well put these things in position space and study
Yeah.
everything. But momentum space, generally in cosmology also, when people look for this correlations, so they do it in momentum space. There's one reason. If you would like to match it to observation, then you should better do it in momentum space. But then what do they do? Actually, you know, what they do is, so this, if this delta phi or whatever has momentum k1, 3 momentum k1, this has 3 momentum k2, this has 3 momentum k3, then this is actually, let me write it as O. So k1, O, k2, O, k3, this correlation functions, and this is given by a triangle where this is k1, this is k2, this is k3. Okay. So there, so what I'm trying to say is, due to homogeneity, if you write down this 3-point function in momentum space, there will be a momentum conserving delta function.
Oh, I see. Okay. Yeah.
Now then this is just saying momentum conservation. K1 plus K2 equals to plus K3 equals to 0. Just implements that delta function here. Now, what in observations, what they do is, it's very hard to kind of see these things in the things. What they do is they take different limits, but this K3 is very small, so that it's almost like a triangle like this. They call it squeezed limit. Or they take one of the momentum very large. So they kind of look for this kind of signatures from the data.
Okay.
So so if we really do it in momentum space, then it becomes very. So now why are we allowed? We are allowed because it's the homogeneity is there. Any constant time slice, you take a time slice here, any time slice, this is almost homogeneous.
Okay,
To
okay.
very large extent.
Thank
So
you,
we
sir.
can use it and then we can match it with observation.
I see. Thanks, sir.
Yeah.
Sorry, one more question.
Sure,
From the
sure.
formula of this lambda operator, is it true that it puts a bound on the mass of the inflaton? I mean, from the square root 9,4 minus m square over h square.
Yes,
Does
yes.
it put a bound on the mass?
Yeah. So what it says is that it doesn't put any bound on the mass of the inflaton in that sense. But
Okay.
let's say if this mass is beyond this and all, so in inflaton, what I probably that's what Devangsu was asking. I didn't answer it that way. So in the QFT in curved space-time point of view, what will happen is that your vacuum will not be stable because you will have, so this is kind of will kind of will kind of signal to some kind of an instability. From the CFT point of view, this delta becomes imaginary, and that also has that kind of signature. So this is kind of borrowed from the ADS-CFT type of.
Okay.
So this is a separate question that probably you are trying to understand or asking me, is that if I'm doing quantum field theory of a scalar field with some mass in curved space-time, is there any bound on that mass?
Yeah.
So yes, this kind of
CFT formalism. Yeah.
yeah. And from the CFT point of view, this delta will be related. But yeah, in the CFT context, this delta plus and delta minus, they will be related by something which is called the shadow transformation. So they fall in some representation of the conformal group and all that stuff. But for us, fortunately, m is 0. So I shouldn't have, I could have cared very less. So if we are looking at the inflaton in the canonical slow roll model, this delta phi, if you remember the action that I wrote at some point here, this is a massless scalar field. So all that you can do is you can also write down some kind of an conformally coupled scalar phi r square type of interaction in the Lagrangian here. That will correspond to delta equal to 2. And this corresponds to delta equals to 3, which is like a marginal operator from the CFT point of view.
Okay.
Okay, if there are no other questions, let us thank Nilay again for the excellent talk. So we will meet again.
Okay, sure.